From space, our planet appears as a blue marble suspended in the cosmic void. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. But look closer at that blue surface, and you will see something remarkable. Thin silver threads wind across every continent like veins carrying life itself. These are Earth's rivers. Every single day, 40,000 cubic kilometers of water moves through these liquid highways. That's enough water to fill Lake Superior 20 times over. The Amazon River alone carries more water to the ocean than the next 7 largest rivers combined. Its mouth is so wide that fresh water flows 200 kilometers out into the Atlantic before salt water finally takes over. Rivers begin their stories in the most unexpected places. High in the Tibetan mountains, a small spring no wider than your bathtub becomes the mighty Yangtze River. This tiny source sits 5,000 meters above sea level, where the air is so thin that every breath carries half the oxygen you're used to. The water that bubbles up here will travel 6,000 kilometers before it tastes salt. But not all rivers start as mountain springs. The longest underground river on Earth flows beneath Mexico's Yucatan Peninsula. For 300 kilometers, this hidden waterway carves through limestone caves in complete darkness. Fish that live here have no eyes at all. They navigate by feeling the gentle currents with sensitive skin that can detect the slightest change in water pressure. Some rivers refuse to follow the rules we expect. In Brazil, the Rio Negro and Amazon River flow side by side for 6 kilometers without mixing. The dark water of the Rio Negro and the sandy brown Amazon maintain their separate identities like two friends walking hand in hand. The difference in temperature, speed, and density keeps them apart until they finally surrender to each other downstream. Rivers carry more than just water on their endless journey to the sea. The Colorado River moves enough sand and rock each year to fill a train stretching from New York to Los Angeles. This grinding, scraping, and carving happens so slowly that a single grain of sand might take 1,000,000 years to travel from the Rocky Mountains mountains to the Gulf of California. Every twist and bend in the river tells the story of stone surrendering to the patient persistence of moving water. The Mississippi River system drains water from 31 states and 2 Canadian provinces. If you dropped a leaf into a stream in Montana, it could theoretically float all the way to the Gulf of Mexico. The journey would take months, carrying that single leaf through forests, farmlands, and cities. Along the way, it would pass through ecosystems that support more than 400 species of fish and 300 species of birds. Deep beneath the Sahara Desert, an ancient river system still flows. The Tamanrasset River ran across North Africa when the Sahara was green and lush 12,000 years ago. Now buried under kilometers of sand, this fossil river continues its underground journey. Scientists can trace its path using satellite imagery that penetrates the sand to reveal the hidden channels carved in bedrock below. Every river on Earth follows the same fundamental law. Gravity pulls each molecule of water toward the lowest point it can find. This simple force creates the intricate branching patterns that look like lightning frozen in the landscape. From the tiniest tributary to the mightiest continental river, water always finds its way home to the sea. The Colorado River began carving the Grand Canyon 6 million years ago. Each year, the river carried away millions of tons of sandstone and limestone. The canyon now stretches 277 miles long and reaches depths of over a mile. To understand this scale, imagine stacking 4 Empire State Buildings on top of each other. That tower would still not reach from the canyon floor to the rim. The Amazon River moves more water than the next 7 largest rivers combined. Every second, it pours 55 million gallons into the Atlantic Ocean. This massive flow creates a freshwater plume that extends 100 miles out to sea. Sailors can drink fresh water from the ocean while still beyond sight of land. The river stretches 4,000 miles from the Peruvian Andes to the Brazilian coast. Ancient rivers shaped every continent on Earth. The Nile has flowed north for 30 million years, carrying fertile soil from the Ethiopian highlands this annual flood cycle, the pyramids would stand in barren wasteland instead of the lush valley that supported Egyptian civilization. The river drops only 1 foot in elevation over its final 1,000 miles. Rivers follow patterns older than mountains. The Mississippi River system drains water from 31 states and 2 Canadian provinces. This network covers 40% of the continental United States. Every raindrop that falls in Montana eventually joins the same flow that carries water from Minnesota and Pennsylvania. The entire system funnels into a single channel at New Orleans. Most rivers are surprisingly young in geological terms. The Great Lakes and their connecting rivers formed only 12,000 years ago when massive ice sheets melted. Before the Ice Age, these river valleys did not exist. The weight of glaciers 2 miles thick carved new pathways for water to follow. Rivers create their own landscapes through constant motion. The Ganges River carries 500 million tons of sediment each year from the Himalayas to the Bay of Bengal. This sediment builds new land at the river mouth faster than the ocean can wash it away. Bangladesh gains 20 square miles of new territory annually from Ganges deposits. Some rivers are older than the continents they cross. The New River in West Virginia flows north through the Appalachian Mountains instead of around them. Geologists believe this river is 300 million years old. The river carved its path before the mountains rose, maintaining its course as the land slowly lifted around it. The mountains grew up through the river rather than blocking its flow. Deep beneath the surface of our planet, water follows paths we cannot see. These hidden rivers began forming millions of years ago when rainwater first touched solid rock. The process starts with a single drop of water absorbing carbon dioxide from the air. This creates weak carbonic acid that slowly dissolves limestone and other soft rocks, grain by grain. Underground rivers carve their channels through complete darkness. The Mammoth Cave system in Kentucky contains over 400 miles of mapped passages. Water created every tunnel and chamber by dissolving rock over millions of years. Some underground rivers flow for hundreds of miles before emerging at natural springs. The water moves through cracks so narrow that only molecules can pass through at first. Time transforms these hairline fractures into flowing waterways. The Dragon's Breath Cave in Namibia holds the largest known underground lake on Earth. This hidden body of water sits 200 feet below the surface and stretches beyond the reach of exploration lights. Scientists believe the lake formed when groundwater collected in a massive limestone chamber carved by ancient rivers. Underground rivers create their own weather systems in the darkness below. The Lost River in Indiana disappears into a cave and travels 23 miles underground before surfacing again. During this hidden journey, the water maintains a constant temperature of 54 degrees regardless of surface weather. These buried waterways never freeze in winter or warm in summer because the Earth's crust insulates them from temperature changes above. Some underground rivers flow upward through solid rock. Artesian springs form when water trapped between rock layers finds a crack that reaches the surface. The water pressure built up over thousands of years forces the river to flow against gravity. The Edwards Aquifer in Texas contains underground rivers that supply water to millions of people. This hidden water system formed when ancient seas covered the region and left behind layers of porous limestone. Underground rivers connect to surface rivers in ways that surprise scientists. The Tamavo River in Italy disappears into a cave and travels 25 miles underground before emerging near the sea. During its hidden journey, the river gains water from dozens of smaller underground streams. These tributary streams formed when surface water found different paths through the rock layers. The birth of underground rivers requires perfect conditions that took millions of years to develop. First, ancient seas deposited limestone and other soluble rocks in thick layers. Then, tectonic forces lifted these rock layers above sea level where rainwater could reach them. Finally, millions of years of patient water flow carved the passages we find today. Each underground river system tells the story of how water shapes the hidden architecture of our planet. These dark waterways continue growing deeper and wider with every drop that flows through them. Water holds secrets that challenge everything we think we know about how rivers behave. The Amazon River sometimes flows backwards during certain seasons when ocean tides push against its current. This backwards flow can travel hundreds of miles inland, carrying salt water and marine sediments into freshwater systems. The phenomenon happens because the Amazon's mouth is so wide and shallow that Atlantic tides create enough pressure to reverse the river's flow. Rivers contain dissolved minerals that traveled billions of miles through space before reaching Earth. Iron particles in river water originated inside massive stars that exploded long before our solar system formed. When these ancient stars died, they scattered iron atoms across the galaxy in brilliant supernova explosions. Gravity eventually pulled these iron atoms into the cloud of dust and gas that became our planet. Now, this stellar iron flows in every river on Earth, connecting mountain streams to the cosmic furnaces where heavy elements were born. The water itself carries an even more amazing story. Scientists believe much of Earth's water arrived on comets and asteroids during a period called the Late Heavy Bombardment. These icy visitors from the outer solar system crashed into our young planet 4 billion years ago. Each impact released tremendous amounts of water vapor that eventually condensed into the first oceans and rivers. The hydrogen atoms in every river drop formed in the first moments after the Big Bang, while the oxygen came from dying stars. River water contains calcium that once formed the shells of ancient sea creatures. When these organisms died millions of years ago, their calcium carbonate shells accumulated on ocean floors and hardened into limestone. Rainwater slowly dissolves this limestone as it flows underground, picking up calcium ions that make water taste slightly mineral. This process explains why some rivers taste different from others, depending on the rock types they encounter during their journey to the sea. Silica particles in river water come from the slow breakdown of granite and other igneous rocks. These tiny glass-like fragments began as molten rock deep in Earth's crust, where intense heat and pressure created quartz crystals. Over millions of years, weather breaks down these crystals into microscopic pieces that rivers carry toward the ocean. The same silica that once formed deep underground now helps build the shells of tiny river organisms called diatoms. Some rivers flow backwards, not because of tides, but because of underground geology. The Jordan River in the Middle East flows northward instead of south because it follows a deep geological crack called the Jordan Rift Valley. This crack formed when tectonic plates slowly pulled apart, creating a pathway that guides water in unexpected directions. The rivers backwards flow relative to most Middle Eastern rivers shows how underground forces shape the paths that water takes across continents. Methane gas bubbles up from some river bottoms, created by ancient organic matter buried in sediment layers. This methane formed when prehistoric plants and animals decomposed without oxygen millions of years ago. The same process that creates natural gas deposits also produces the bubbles that sometimes make river water appear to sparkle. Rivers carry these gases downstream, connecting the carbon cycle of ancient forests to the atmosphere of today. Every bubble represents organic matter that once lived and breathed on a very different version of Earth. Moving water transforms everything it touches through invisible chemical forces that work like tiny molecular hands. Oxygen dissolves into river water as it tumbles over rocks and falls, creating the conditions that allow fish and plants to breathe underwater. This dissolved oxygen comes from the air above and from photosynthesis by microscopic algae that drift in the current. The faster a river flows, the more oxygen it can hold, which explains why mountain streams support different life than slow-moving lowland rivers. Carbon dioxide also dissolves into river water, but this gas creates a gentle acid that slowly eats away at limestone and marble. This process, called chemical weathering, happens so gradually that you cannot see it. But over thousands of years, it carves enormous caves and canyons. The Colorado River carved the Grand Canyon not just by carrying away sand and pebbles, but by chemically dissolving the rock itself. Every drop of river water contains tiny amounts of carbonic acid that work like molecular sculptors, reshaping the landscape one atom at a time. Rivers carry dissolved minerals picked up from the rocks they flow over, creating a liquid soup of calcium, magnesium, and iron. These dissolved minerals give each river its unique chemical fingerprint. Scientists can identify which mountain range a river flows from just by testing the minerals in its water. When rivers reach the ocean, these minerals become part of the salt that makes seawater taste different from fresh water. Temperature controls how much of each chemical a river can hold, like invisible storage containers that change size with heat and cold. Hot water dissolves more minerals than cold water, which explains why rivers flowing from volcanic regions often taste metallic or sulfurous. The Yellowstone River carries dissolved sulfur compounds from underground hot springs, giving it a distinctive smell that comes from chemical reactions happening deep beneath the earth. Cold mountain rivers hold more dissolved oxygen but fewer minerals, creating crystal clear water that supports different types of life. pH levels in rivers determine which chemicals can exist together without forming solid particles that sink to the bottom. Acidic rivers can dissolve metals like iron and copper, carrying them downstream as invisible dissolved particles. When these metal-rich waters mix with less acidic water, the metals suddenly become visible again, forming colorful deposits along riverbanks. The Rio Tinto in Spain flows bright red because it carries so much dissolved iron that it looks like liquid rust. Biological chemistry happens when bacteria in river water break down organic matter, releasing nutrients that feed plants and algae downstream. These bacteria consume oxygen as they work, which can create dead zones in slow-moving rivers where fish cannot survive. The process connects the chemistry of decay to the chemistry of growth. As nutrients released from dead leaves become food for living plants, rivers transport these chemical cycles across entire continents, carrying the building blocks of life from forests to to farmlands, to oceans. Seasonal changes alter river chemistry as spring snowmelt dilutes mineral concentrations, while autumn leaf fall increases organic acids. This chemical rhythm affects everything from the taste of drinking water to the types of insects that can survive in the current. Rivers become living laboratories where chemistry experiments have been running continuously for millions of years. Each chemical reaction in moving water connects to countless others, creating an invisible network of molecular interactions that shapes the world around us. The chemistry of rivers writes the story of our planet in a language of dissolved minerals and flowing reactions. Some rivers never reach the ocean. They flow for hundreds of miles through desert landscapes, carrying snowmelt from distant mountains until the sand swallows every drop. The Okavango River in Africa travels over 1,000 miles from Angola's highlands, only to vanish completely into the Kalahari Desert. This massive river system creates the world's largest inland delta, spreading across an area the size of Switzerland. The water doesn't disappear instantly. It seeps slowly through layers of sand and clay, creating underground reservoirs that can stretch for miles beneath the surface. Scientists call these vanishing rivers endorheic systems, meaning they drain into closed basins rather than flowing to the sea. The scale of water loss amazes researchers who study these systems. A river carrying enough water to fill a swimming pool every second can completely disappear within just 50 miles of desert travel. The sand acts like an enormous sponge, absorbing water through countless tiny spaces between individual grains. Each grain of sand can hold a thin film of water around its surface, and billions of grains create vast underground storage systems. Temperature plays a role in these disappearing acts. Desert air can steal water through evaporation at rates that seem impossible in cooler climates. A single square mile of river surface in the Sahara can lose over 2 million gallons of water per day to evaporation alone. The combination of blazing sun and bone-dry air creates conditions where water molecules escape into the atmosphere faster than the river can replace them. Some desert rivers lose more water to evaporation than they do to underground seepage, especially during the hottest months of summer. The Colorado River once flowed all the way to the Gulf of California, carrying snowmelt from the Rocky Mountains across 1,000 miles of increasingly dry landscape. Today, this mighty river often disappears completely before reaching the ocean, absorbed by irrigation systems and desert sands along its journey. The last 100 miles of the Colorado's historic channel now lie empty most years, filled only with wind-blown sand and scattered stones. When viewed from space, satellite images show the river's path simply ending in a maze of dry channels that spread across the desert like the fingers of an outstretched hand. Underground, these vanished rivers continue their journey in slow motion. Water that disappears into desert sand doesn't simply evaporate away. Much of it joins vast aquifer systems that can stretch for hundreds of miles beneath the surface. These underground rivers move incredibly slowly, sometimes traveling just a few feet per year through layers of sandstone and limestone. Scientists have discovered that water currently flowing in some desert aquifers fell as rain thousands of years ago, when these regions had different climates. The Mojave River in California demonstrates this phenomenon on a scale that surprises visitors who expect to see flowing water. This river flows above ground for only short stretches during wet years, spending most of its length hidden beneath sandy washes and rocky channels. During rare flood years, the entire river system can reappear overnight, transforming dry desert valleys into rushing torrents that carry decades worth of accumulated debris toward distant dry lakes. These temporary resurrections remind us that even vanished rivers maintain their ancient pathways, waiting patiently beneath the sand for the next big storm to bring them back to life. The scale of water storage in desert sands exceeds what most people imagine possible. Beneath Australia's Great Western Desert, disappeared rivers have created underground water reserves that contain more fresh water than some of the world's largest surface lakes. These hidden reservoirs formed over millions of years as ancient rivers repeatedly vanished into the sand, leaving behind their liquid legacy in underground chambers and porous rock formations. The water waits in darkness, some of it so old that it predates human civilization, preserved in stone vaults that may never again see sunlight. Some rivers never flow as liquid water at all. These frozen rivers of ice move with the patience of geological time, carving valleys and shaping continents, grain by grain. The Hubbard Glacier in Alaska advances toward the sea at roughly 6 feet per day, its surface crackling and groaning as ancient ice compressed over centuries finally reaches the ocean. The ice carries stories from decades past, trapping bubbles of air from years when the atmosphere held different amounts of carbon dioxide. Glacial rivers flow in ways that defy our normal understanding of water movement. The Lambert Glacier in Antarctica stretches for over 250 miles, making it longer than many traditional rivers. Yet it moves at the speed of growing fingernails. Its surface appears solid and still, but beneath that frozen exterior lies a river of ice flowing toward the sea with unstoppable momentum. The glacier carries rocks and boulders like a conveyor belt made of ice, transporting mountain debris hundreds of miles from its source. These ice rivers create their own weather systems as they flow. The Perito Moreno Glacier in Argentina generates its own winds as cold air flows down from its surface, creating microclimates that can be felt for miles around. When chunks of glacier ice crash into the water below, they produce sounds that travel through the ice for dozens of miles. Scientists can listen to these glacial conversations using sensitive microphones, hearing the ice speak in frequencies too low for human ears to detect naturally. The surface of a flowing glacier tells the story of its journey through texture and color. Medial moraines create dark stripes down the center of glaciers, where two ice streams merge, carrying different collections of rock and debris. These stripes remain distinct for the entire length of the glacier, never mixing despite flowing together for decades. The ice itself ranges from brilliant white, where air bubbles reflect light, to deep blue, where the ice has been compressed so tightly that it absorbs red wavelengths and reflects only blue. Some glacial rivers flow faster than others, creating dramatic surface features. The Jakobshavn Glacier in Greenland moves so quickly that its surface constantly cracks and reforms, creating a landscape of ice towers and deep crevasses that change daily. This glacier flows at speeds of up to 150 feet per day during summer months, making it one of the fastest moving ice rivers on Earth. The constant motion creates a surface that resembles a frozen ocean caught mid-wave, with ridges and valleys that shift and change as the ice flows toward the sea. Ancient ice rivers preserve climate records spanning hundreds of thousands of years. The ice in Antarctica's glaciers contains air bubbles from atmospheres that existed when woolly mammoths roamed the earth. Scientists can read these frozen libraries like tree rings, discovering what the air was like during ice ages and warm periods throughout Earth's climate history. Each layer of ice represents a year of snowfall, compressed and preserved in a flowing archive that moves slowly toward the ocean while maintaining its historical record. The termination of ice rivers creates some of the most dynamic landscapes on Earth. When glacial ice reaches the ocean, it doesn't simply melt away quietly. Instead, it calves off in massive chunks that can be larger than city blocks, creating icebergs that will drift in ocean currents for months or years. These ice rivers continue their journey even after leaving land, carrying fresh water and ancient air bubbles thousands of miles from their mountain sources. The process connects the highest peaks with the deepest ocean basins, completing a cycle that began with snowflakes falling on distant mountains decades or centuries ago. Rivers create their own music as water moves through different landscapes and obstacles. The sound changes dramatically based on what lies beneath the surface. Fast water rushing over rocks produces a bright, chattering melody, while slow water moving through deep pools creates barely audible whispers. Scientists have discovered that the frequency of river sounds depends on the size of the stones and sediment on the riverbed. Small pebbles create high-pitched tinkling sounds as water bounces between them. Larger boulders produce deeper, more resonant tones that can travel for miles through river valleys. The water itself acts like a musical instrument, with the riverbed serving as the strings and the flowing current as the bow. Each river develops its own unique acoustic signature based on the geology it encounters along its path. The music changes with the seasons as water levels rise and fall. During spring floods, rivers roar with the deep bass notes of massive water volumes moving at high speed. Summer brings quieter melodies as water levels drop and expose more of the rocky riverbed. Winter often silences the music entirely as ice forms over the surface, muffling the sounds beneath. Underground rivers create entirely different acoustic environments. Water flowing through cave systems produces echoing sounds that can resonate for hundreds of feet through limestone chambers. The pitch and tone depend on the size of the cave passages and the speed of the underground current. Some cave rivers flow so quietly they can only be detected by the subtle sound of water dripping from stalactites into hidden pools. Rivers also generate infrasound frequencies too low for human ears to detect. These deep vibrations travel through the ground and can be felt by animals long before the river becomes visible. Elephants and other large mammals use these subsonic river sounds to navigate toward water sources during dry seasons. The infrasound carries information about water depth, flow rate, and even the type of substrate the river is flowing over. The temperature of water affects the sounds rivers make. Cold water from mountain snowmelt creates sharper, more crystalline sounds as it flows over rocks. Warmer water produces softer, more muffled tones because heat changes how sound waves travel through the liquid. Some rivers in volcanic regions carry water heated by underground thermal sources, creating unique acoustic properties as the warm current mixes with cooler tributary streams. Rivers flowing through different types of rock create distinct sound patterns. Sandstone channels produce softer, more absorbed sounds because the porous rock dampens vibrations. Granite riverbeds create bright, ringing tones that echo off the hard surfaces. Limestone rivers often sound hollow and resonant because the water has carved smooth, curved channels through the soluble rock over thousands of years. The music of rivers connects to the larger orchestra of natural sounds in each ecosystem. Bird songs, wind through trees, and insect calls blend with the water's melody to create unique soundscapes that change throughout the day and across seasons. These acoustic environments have remained largely unchanged for thousands of years, providing a constant backdrop to the evolution of life along riverbanks. Deep in the Amazon rainforest, some rivers create their own gentle light show every night. Tiny organisms called dinoflagellates drift in the water, flashing bright blue whenever the current disturbs them. These microscopic creatures contain a chemical called luciferin that reacts with oxygen to produce cold light. The same process happens in fireflies, but these water dwellers create a softer, more sustained glow that pulses with the river's movement. Scientists believe this bioluminescence evolved as a defense mechanism. When a fish or other predator disturbs the water, the sudden flash of light might startle the attacker or attract larger predators to the scene. The timing follows predictable cycles tied to water temperature and nutrient levels. Warmer months bring more intense displays because the organisms reproduce faster in heated water. Rivers in New Zealand's caves showcase a different type of natural illumination. Glowworms hang from the rocky ceilings, creating constellations of blue-green light reflected in the dark water below. These creatures spend most of their lives as larvae, spinning silk threads to catch flying insects. The light comes from a chemical reaction in their tails, designed to lure prey into their sticky traps. The cycles of river bioluminescence connect to larger patterns in nature. Tidal rivers experience the strongest displays during new moon phases when the water is darkest. Ocean currents bring fresh nutrients upstream, feeding the glowing organisms and creating spectacular light shows that can stretch for miles. These displays peak during certain seasons when temperature and salinity levels reach optimal conditions. Some rivers glow not from living organisms, but from dissolved minerals. Thermal springs in Yellowstone create rivers that shimmer with natural fluorescence under ultraviolet light. The dissolved minerals absorb invisible UV rays from sunlight and re-emit them as visible colors. Copper compounds create blue-green glows, while sulfur produces yellow tints that shift and dance with the flowing water. Arctic rivers develop their own seasonal light cycles during the long polar nights. Ice crystals in the water catch and scatter light from the aurora borealis, creating rivers that seem to flow with captured starlight. The moving water prevents complete freezing, allowing these light patterns to shift and change throughout the winter months. Indigenous peoples have observed these phenomena for thousands of years, weaving them into stories about rivers that carry the spirits of ancestors. The chemistry behind natural river illumination involves complex cycles of energy transfer. Organisms absorb energy from their food or from chemical reactions, then release it as light through specialized cells called photophores. This process is remarkably efficient, producing almost no heat waste. Unlike artificial lighting, the light output varies with water chemistry, temperature, and the availability of dissolved oxygen. Rivers that glow demonstrate the intricate connections between water chemistry, living organisms, and light itself. These natural light shows remind us that even in darkness, rivers continue their ancient work of connecting ecosystems and carrying life from source to sea. The ancient dance between neighboring waters reveals one of nature's most striking phenomena. When the Rio Negro meets the Amazon River near Manaus, Brazil, their waters flow side by side for nearly 4 miles without mixing. The dark, tea-colored Rio Negro carries different minerals and temperatures than the sandy brown Amazon. These chemical and physical differences create an invisible barrier that keeps the rivers separate even as they share the same channel. Temperature plays a role in this aquatic standoff. The Rio Negro flows at around 79 degrees Fahrenheit, while the Amazon runs cooler at 73 degrees. Warmer water is less dense than cooler water, creating layers that resist mixing. The speed difference also matters tremendously. The Amazon rushes along at nearly 4 miles per hour while the Rio Negro moves more slowly at about 1.5 miles per hour. Scientists call this phenomenon a confluence, but the word barely captures the complexity of what happens when river systems meet. The Rio Negro carries dissolved organic compounds from decomposing vegetation in the rainforest. These tannins give the water its dark coffee color and slightly acidic chemistry. The Amazon carries heavy loads of sediment from the Andes Mountains, creating its characteristic muddy appearance. Similar meetings occur around the world wherever rivers with different characteristics converge. In Switzerland, the Rhone and Arve rivers maintain distinct colors for miles after joining near Geneva. The Rhone carries glacial flour, tiny particles of rock ground down by moving ice. This gives the water a distinctive milky blue-green color that contrasts sharply with the clear Arve. The chemistry behind these separations involves more than just visible differences. Rivers carry dissolved salts, minerals, and organic compounds that create unique chemical signatures. When waters with different pH levels meet, they can remain separate for surprising distances. The Amazon system alone demonstrates this principle across thousands of miles as tributaries join the main stem. Seasonal changes can dramatically alter these mixing patterns. During flood season, increased water volume and turbulence can force mixing that normally takes miles to occur. The boundary between the Rio Negro and Amazon shifts and wavers like a living thing. Local fishermen have learned to read these patterns, knowing that different fish species prefer different water types. The phenomenon extends beyond South America to rivers across every continent. In Alaska, rivers carrying different types of glacial melt create spectacular color contrasts. Some carry rock flour that creates turquoise water, while others remain clear. These meetings create natural laboratories where scientists can study how water chemistry affects aquatic ecosystems. The mixing process eventually wins, but it happens gradually through molecular diffusion and turbulence. Tiny eddies and currents slowly exchange water between the two streams. Temperature differences equalize first, followed by the gradual mixing of dissolved substances. by the time these combined waters reach the ocean, they carry the blended signature of their entire watershed. The refusal to mix becomes acceptance, and separate rivers become one unified flow, carrying the stories of all the lands they have touched. The smallest rivers on Earth measure just a few feet from bank to bank, yet they carry the same ancient purpose as their massive cousins. In the mountains of Montana, streams barely 3 feet wide begin their journey toward the Missouri River system. These miniature waterways start as springs bubbling up from underground aquifers that have been storing water for decades. The water emerges at a constant temperature year-round, creating tiny oases of life in harsh alpine environments. Some of the world's shortest rivers flow for less than 100 feet before joining larger waterways. The Roe River in Montana holds the official record at just 200 feet long, though seasonal variations can shrink it to half that distance. Despite its tiny size, this river supports populations of trout and provides drinking water for local wildlife. The shortest rivers often carry the purest water because they have little time to collect pollutants or sediments. Underground streams create some of Earth's most extreme river systems, flowing through caverns so narrow that only cave fish can navigate them. These subterranean waterways sometimes measure less than 2 feet wide, but extend for miles through solid rock. The water moves incredibly slowly, taking years to travel distances that surface rivers cover in hours. Cave rivers maintain constant temperatures and create unique ecosystems where blind fish and transparent crustaceans have evolved over millions of years. The fastest rivers on Earth reach speeds that would terrify any swimmer brave enough to enter their waters. Rapids in the Colorado River through the Grand Canyon can exceed 30 miles per hour during peak flow periods. These extreme velocities occur when massive volumes of water squeeze through narrow canyon passages carved over millions of years. The kinetic energy in fast-moving water can move boulders weighing several tons, reshaping riverbeds with each major flood event. At the opposite extreme, some rivers move so slowly they appear appear motionless to casual observers. The Everglades in Florida contains rivers that flow at speeds measured in feet per day, rather than miles per hour. This sheet flow system moves water across vast wetlands at a pace so gentle that it barely disturbs floating vegetation. These slow rivers create perfect conditions for water filtration, as plants and sediments have time to remove impurities from the flowing water. The coldest rivers maintain temperatures just above freezing, even during summer months. Glacial streams in Alaska and Greenland carry water so cold that it numbs exposed skin within seconds. These frigid waterways support unique species of fish that have adapted to near-freezing conditions by producing natural antifreeze proteins in their blood. The coldest recorded river temperature was measured in Siberia at just 2 degrees above freezing during the height of summer. Desert rivers represent another extreme, appearing and disappearing based on rare rainfall events. These ephemeral waterways can transform from bone-dry channels to raging torrents within hours of a desert storm. Flash floods in these systems can reach depths of 20 feet and speeds exceeding 40 miles per hour. The water carries enormous amounts of sand and debris, scouring canyon walls and depositing sediments miles downstream before disappearing back into the desert floor. The highest rivers on Earth flow at altitudes where the air contains half the oxygen found at sea level. Rivers in the Himalayas begin their journey above 18,000 feet, where water boils at lower temperatures due to reduced atmospheric pressure. These extreme altitude waterways freeze solid for months each year, storing water as ice until spring melting releases torrents that feed major river systems across Asia. The combination of extreme cold, low oxygen, and intense ultraviolet radiation creates conditions unlike anywhere else on Earth. Yet these rivers support specialized communities of microorganisms that thrive in these harsh environments. Water sometimes defies gravity in ways that seem impossible. The Jordan River actually flows uphill for several miles near its source, climbing gradually as it moves through underground limestone channels that create natural siphon effects. This phenomenon occurs when water pressure builds up in confined underground spaces, forcing the river to rise against gravity's pull. Scientists have measured sections where the Jordan climbs nearly 40 feet over a distance of 3 miles, creating one of nature's most puzzling hydraulic mysteries. Rivers can flow backward when tidal forces overcome their natural current. The Amazon River reverses its flow for hundreds of miles inland twice each day during spring tides. Ocean water pushes so far upstream that fresh water actually flows backward toward the mountains for several hours. This tidal bore creates waves that travel upstream at speeds reaching 20 miles per hour, carrying salt water deep into the rainforest where it mixes with fresh mountain runoff. Some rivers appear to flow uphill due to optical illusions created by the surrounding landscape. The Electric Brae in Scotland hosts a stream that seems to defy gravity, flowing upward along a gentle slope. The surrounding hills create a visual reference that tricks the human eye into perceiving upward flow when water actually moves downhill. Magnetic hill phenomena occur worldwide, where rivers appear to climb slopes due to the absence of proper horizontal reference points in the terrain. Underground rivers sometimes emerge at elevations higher than their source points. The Timavo River in Italy disappears into limestone caves and resurfaces 25 miles away at an elevation 60 feet higher than where it vanished. Underground pressure systems and artesian aquifers create enough force to push water upward through rock formations. These subterranean hydraulic systems can maintain pressure for decades, storing water in underground chambers before releasing it at higher elevations through natural springs. Thermal differences can cause rivers to flow against their normal gradient. Hot springs create density differences that push heated water upward through rock fractures, sometimes emerging hundreds of feet above the original water table. The Mammoth hot springs in Yellowstone demonstrate this principle, where superheated groundwater rises through limestone and emerges at elevations far above nearby cold water sources. temperature variations of just 20 degrees can create enough buoyancy to lift water vertically through narrow underground channels. Atmospheric pressure changes can temporarily reverse river flow in low-lying areas. During severe weather systems, barometric pressure drops can reduce the weight of air pressing down on river surfaces. This reduction allows underground pressure to push water backward through river channels for short periods. The phenomenon occurs most dramatically in river deltas, where the elevation change between source and mouth creates minimal gravitational pull on the water. Capillary action enables tiny amounts of river water to climb vertical surfaces. Water molecules cling to each other, and to rock surfaces with enough force to pull streams of moisture several inches up canyon walls. This molecular adhesion creates miniature waterfalls that appear to flow upward along cliff faces. The same forces that allow plants to draw water from soil to leaves enable rivers to deposit moisture at elevations above their main channel through microscopic surface tension effects. The first explorers to study river colors made a simple mistake. They assumed all water should look the same. Early naturalists in the 1600s believed that pure water had no color at all. They thought colored rivers were somehow contaminated or unnatural. This misconception lasted for centuries because most European rivers ran brown with soil and debris. When Spanish conquistadors first saw the Rio Negro in South America, they named it Black River. The water appeared almost black against the bright green jungle. They had no instruments to measure what caused this darkness. Local indigenous people tried to explain that the water came from rotting leaves, but the explorers dismissed this as superstition. The breakthrough came in 1859 when German naturalist Alexander von Humboldt developed the first scientific method for studying river colors. He collected water samples in clear glass bottles and compared them against white paper backgrounds. This simple technique revealed that river color came from dissolved minerals and organic matter, not contamination. Humboldt discovered that tannic acid from decomposing vegetation created the tea-colored waters of tropical rivers. The same compounds that make tea brown were seeping from fallen leaves and bark into river systems. This organic staining could make water look like dark coffee while remaining perfectly safe to drink. Glacial rivers puzzled scientists for decades because of their unusual milky appearance. Early geologists thought the cloudiness came from air bubbles trapped in melting ice. They spent years trying to filter out these imaginary bubbles before realizing the truth. The mystery was solved in 1876 when Swiss glaciologist Louis Agassiz examined glacial flour under a microscope. He found that glaciers grind bedrock into particles so fine they remain suspended in water for weeks. This rock dust creates the distinctive milky blue-green color of glacial rivers. Red rivers presented another puzzle that took decades to solve when American geologist John Wesley Powell first descended the Colorado River in 1869. He noted how the water changed from clear to deep red as it flowed through different rock layers. He initially believed the color came from iron ore dissolved in the water. Powell's team collected red water samples and let them sit for days. They watched heavy particles sink to the bottom, leaving clear water above. This simple experiment proved that red rivers get their color from suspended clay and silt, not dissolved minerals. The discovery of truly blue rivers challenged everything scientists thought they knew about watercolor. When explorers reached the Blue Danube in the 1800s, they expected to find copper compounds causing the blue tint. Instead, they found something far more interesting. Blue rivers occur when water contains almost no suspended particles at all. The water appears blue for the same reason the sky looks blue. Light scatters differently through pure water, emphasizing blue wavelengths while absorbing reds and yellows. Scientists in the early 1900s developed the first color measurement scales for rivers. They created standardized charts comparing water samples to colored glass plates. This system allowed researchers around the world to communicate precise color observations for the first time. The most dramatic discovery came when explorers found rivers that changed colors with the seasons. The Caño crystals in Colombia shifts from clear to brilliant red, yellow, and green, depending depending on water levels and algae growth. Early visitors thought they were seeing different rivers entirely. Modern spectroscopy finally revealed the complete science behind river colors in the 1950s. Scientists could now measure exactly which wavelengths of light each river absorbed or reflected. They discovered that even the clearest mountain streams contain trace minerals that subtly shift their color toward blue or green. Today, we know that river color tells the story of everything the water has touched. Each hue reveals the rocks it has carved, the plants it has passed, and the soil it has carried on its long journey to the sea. Deep beneath the ocean floor, rivers flow in complete darkness through networks of rock and sediment. These submarine groundwater systems carry fresh water for hundreds of miles under the seafloor before emerging as underwater springs. Scientists discovered these hidden rivers by accident in the 1970s when deep-sea drilling equipment brought up fresh water samples from areas thousands of miles from any coastline. The water had traveled underground for centuries, following ancient riverbeds that were buried when sea levels rose. Some of these buried rivers maintain their original channels perfectly preserved in rock. The Connecticut River once flowed through what is now the middle of the Atlantic Ocean during the last ice age. When glaciers melted and seas rose, the river channel became entombed beneath layers of marine sediment. Today, that same water pathway still carries groundwater eastward under the ocean, emerging as freshwater seeps on the continental shelf. The Amazon River creates an underwater river of its own making where it meets the Atlantic Ocean. The river's tremendous flow pushes a layer of fresh water far out to sea, creating a distinct boundary with the saltwater below. This underwater river of Amazon water travels over 100 miles into the ocean before finally mixing completely. Sailors have drawn fresh drinking water from the ocean surface while floating directly above the salty depths. Even stranger are the rivers that flow upward through the ocean floor. Hydrothermal vents create reverse rivers where superheated water shoots up from deep within the Earth's crust. These underwater geysers carry dissolved minerals and gases that have been cooking in underground chambers for thousands of years. The water emerges at temperatures over 400 degrees Fahrenheit, hot enough to melt lead, yet it cannot boil because of the immense pressure at those depths. Antarctica hides rivers flowing beneath miles of solid ice. Lake Vostok, buried under 2 miles of ice, feeds a network of subglacial rivers that flow toward the ocean. These rivers have been flowing in total darkness for millions of years, carrying water that last saw sunlight when dinosaurs walked the earth. The water stays liquid because of geothermal heat from the planet's core and the insulating effect of the massive ice sheet above. The most surprising underwater rivers exist in places where no surface water flows at all. The Sahara Desert sits above enormous underground river systems that dwarf any surface river on Earth. These fossil water aquifers contain water that fell as rain over 10,000 years ago when the Sahara was green and lush. The water flows slowly eastward through porous rock, traveling just a few feet per year on a journey that takes millennia to complete. Deep ocean trenches contain rivers of dense, cold water that flow along the seafloor like liquid mercury. These bottom currents carry water from polar regions toward the equator, moving so slowly that a single drop takes over 1,000 years to complete the journey. The water is so dense from cold temperatures and high salt content that it behaves almost like a separate liquid flowing beneath the regular ocean water above. These underwater rivers help regulate the planet's climate by carrying cold water from the poles to warm tropical seas, creating a global circulation system that has operated unchanged for millions of years. Rivers possess an almost magical ability to completely change their course across the landscape. The Mississippi River has wandered back and forth across Louisiana like a restless giant, abandoning old channels and carving new ones every few centuries. Scientists call this process avulsion, when a river suddenly decides to flow in an entirely different direction. The old channel becomes a crescent-shaped lake called an oxbow, while the river begins its new path through previously dry land. This wandering behavior connects rivers to the very pulse of the planet, mountains rise due to tectonic forces deep underground. Rivers respond by cutting deeper channels or finding new routes around the obstacles. The Colorado River carved the Grand Canyon, not because the land sank, but because the entire Colorado Plateau slowly lifted upward over millions of years. The river kept cutting downward as the land rose beneath it, creating one of Earth's most spectacular displays of geological time. Climate changes trigger massive shifts in river behavior across entire continents. During ice ages, rivers freeze solid for thousands of years, then suddenly roar back to life as glaciers melt. The channeled scablands in Washington state show the scars of one such awakening. When an ice dam broke at the end of the last ice age, it released a flood larger than all current rivers combined. This single event carved canyons hundreds of feet deep in just a few days. Ocean levels directly control how rivers behave near coastlines. When sea levels drop during ice ages, rivers cut deeper channels as they chase the retreating shoreline. When oceans rise, rivers slow down and deposit massive amounts of sediment, building deltas that can extend hundreds of miles into the sea. The Amazon River's influence reaches so far into the Atlantic Ocean that fresh water can be detected over 100 miles from shore. Underground water systems create invisible connections between rivers separated by vast distances. The Ogallala Aquifer beneath the Great Plains connects groundwater from 8 different states, feeding springs that become rivers thousands of miles apart. When this underground reservoir drops, rivers across the entire region begin to shrink simultaneously, showing how deeply interconnected these water systems truly are. Volcanic activity can instantly redirect rivers across entire mountain ranges. When Mount Mazama erupted to create Crater Lake, it completely rerouted several rivers that had flowed in the same direction for millions of years. The lava flows acted like giant dams, forcing the water to find new paths through the landscape. Some rivers disappeared entirely, while others doubled in size as they inherited the flow from their buried neighbors. Rivers also respond to changes in vegetation across their watersheds. When forests grow thick, they slow down rainfall and release water gradually through their roots. When forests disappear, the The same rainfall creates sudden floods that can permanently alter a river's course. The Amazon rainforest actually helps create its own rivers by recycling moisture from the Atlantic Ocean through countless cycles of evaporation and rainfall. Seasonal changes create predictable patterns in how rivers shift their channels. Spring snowmelt brings massive volumes of water that carve new channels, while summer droughts expose sandbars that redirect the flow. Over decades, these seasonal cycles cause rivers to migrate slowly across their floodplains, creating the serpentine patterns visible from space. The gravitational pull of the moon affects rivers just as it affects ocean tides. Large rivers like the Amazon actually experience tidal bores that travel hundreds of miles upstream, temporarily reversing the flow direction. These tidal influences can cause rivers to change their behavior in subtle but measurable ways, connecting the flow of fresh water to the same cosmic forces that move the seas. Human activities have accelerated natural river changes in unexpected ways. When we remove water for irrigation or dam construction, rivers respond by cutting deeper channels or abandoning sections entirely. The Colorado River now rarely reaches the ocean because so much water is diverted along its path. Yet, even these changes follow the same natural laws that have governed river behavior for billions of years, showing how all water systems remain connected in an endless cycle of movement and change. High above the surface of our planet, invisible rivers flow through the atmosphere with the same persistence as the waterways below. These atmospheric rivers carry more water than the Amazon, moving moisture from tropical oceans toward distant continents in narrow bands that stretch thousands of miles. Scientists discovered these aerial highways only recently, using satellites to track the movement of water vapor through the sky. A single atmospheric river can transport 15 times the volume of the Mississippi River, yet remain completely invisible to the naked eye. The warm Pacific Ocean feeds these sky rivers with endless evaporation, sending columns of moisture northward along predictable paths. When these invisible streams encounter mountain ranges, they release their cargo as rain or snow, sometimes dumping several feet of precipitation in just a few days. California receives nearly half of its annual water supply from atmospheric rivers that originate near Hawaii. The same process that carved the Grand Canyon through millions of years now delivers fresh water to cities and farms through these aerial channels. Climate change has begun altering the behavior of atmospheric rivers in ways scientists are still learning to understand. Warmer air holds more moisture, making these invisible rivers more powerful and unpredictable than they were centuries ago. Some atmospheric rivers now carry twice as much water as they did 50 years ago, leading to more intense flooding when they make landfall. Yet the same systems that bring destructive floods also end droughts, showing how the atmosphere balances water distribution across vast distances. The jet stream acts like a guide for these aerial waterways, steering them toward different regions as it shifts with the seasons. During winter months, atmospheric rivers typically aim toward the Pacific Northwest, bringing the heavy rains that feed the region's massive forests. Summer patterns redirect these moisture streams toward different latitudes, creating the monsoon seasons that billions of people depend on for agriculture. The timing of these shifts has remained remarkably consistent for thousands of years, creating predictable wet and dry seasons that shape entire ecosystems. Ancient civilizations unknowingly planned their agricultural cycles around the arrival of atmospheric rivers, planting crops to coincide with moisture delivery from distant oceans. The Nile River's annual floods, which sustained Egyptian civilization for millennia, were fed by atmospheric rivers that carried water from the Indian Ocean across Africa. Modern weather prediction relies on tracking these invisible streams to forecast rainfall weeks in advance. Satellites can now see the water vapor signatures of atmospheric rivers forming over the ocean, allowing meteorologists to predict when and where they will make landfall. The connection between ocean temperatures and atmospheric river behavior reveals how all of Earth's water systems respond to the same underlying forces. When Pacific waters warm during El Niño events, atmospheric rivers become stronger and more frequent, bringing excessive rainfall to some regions while leaving others in drought. These patterns repeat in cycles that span decades, showing how the planet's water distribution changes slowly over time. The same solar energy that drives ocean currents also powers the evaporation that feeds atmospheric rivers, connecting the movement of water from the deepest ocean trenches to the highest layers of the atmosphere. Scientists now recognize that atmospheric rivers have been shaping Earth's climate and geography for millions of years, long before humans existed to name them. These invisible streams carved river valleys by delivering the precipitation that fed glaciers during ice ages. They transported moisture across continents, creating the rainfall patterns that determined where forests grew and deserts formed. Today, as we track these aerial waterways with sophisticated instruments, we discover that the sky above us flows with the same eternal rhythms that have guided water across our planet since the oceans first formed, connecting every raindrop to the vast circulation of moisture that sustains all life on Earth. The same solar energy that drives atmospheric rivers also heats the Earth's surface in ways that create some of the most extraordinary water phenomena on our planet. In Iceland, rivers flow directly over volcanic rock, so hot that the water begins to steam and bubble before it even reaches the surface. These thermal rivers carry temperatures that would scald human skin, yet they support unique forms of life that thrive in conditions most organisms cannot survive. The boiling river of Peru winds through the Amazon rainforest like a ribbon of liquid fire. Local people call it Shanade Impishka, which means boiled with the heat of the sun. The water reaches temperatures of nearly 200 degrees Fahrenheit, hot enough to cook an egg or brew tea. Scientists believe the river's heat comes from geothermal activity deep beneath the rainforest floor, where the Earth's internal energy rises through cracks in the bedrock. When sunlight strikes these steaming waters, it creates optical effects that seem almost magical. The hot water vapor rises and cools rapidly in the jungle air, forming dense clouds of mist that catch and scatter light in brilliant rainbows. The steam itself becomes a canvas for the sun's rays, painting colors across the forest canopy that shift and dance with every breeze. In Yellowstone National Park, the Firehole River flows through a landscape where underground heat sources warm the water year-round, even in the depths of winter, when snow blankets the surrounding mountains. This river remains warm enough that ice never forms along its banks. The contrast creates scenes of stunning beauty, where steam rises from open water while everything else lies frozen under layers of white. The light that filters through these rising columns of steam carries information about the water's chemical composition. Minerals dissolved from deep rock formations give each thermal river its own unique signature when viewed through the spectrum of scattered sunlight. Iron creates reddish hues in the steam, while sulfur compounds add yellow tints that glow like captured sunshine. Some of these heated rivers flow so consistently that they have carved their own microclimates. Plants that normally grow in tropical regions flourish along the banks of thermal streams in otherwise temperate or even Arctic environments. The warm water creates pockets of humidity and elevated temperatures that extend for hundreds of yards beyond the river's edge. The interaction between hot water and cold air produces convection currents that can be seen when light passes through them. These invisible columns of rising air bend and distort light rays, creating the wavy, dancing effect that makes distant objects appear to shimmer and move. The phenomenon occurs because hot air is less dense than cold air, causing light to travel through layers of different densities at varying speeds. In Russia's Kamchatka Peninsula, entire river systems flow through valleys heated by underground volcanic activity. The Valley of Geysers contains rivers that maintain temperatures above freezing even when the surrounding landscape experiences temperatures far below zero. These thermal rivers create their own weather patterns, generating localized fog banks and cloud formations that can be seen from space. The minerals carried by these superheated waters often precipitate out as the temperature drops, creating natural sculptures along the riverbanks. Calcium carbonate builds up in terraced steps, while silica creates smooth, glass-like surfaces that reflect light like natural mirrors. These formations grow slowly over thousands of years, shaped by the constant flow of mineral-rich water thermal rivers eventually cool and join regular waterways, they carry with them the chemical signatures of their underground journey. The mixing zone creates temperature gradients that can be detected by satellites, showing how deep Earth processes influence surface water systems across vast distances. These heated waterways remind us that our planet's surface and interior remain connected through the endless circulation of water, energy, and dissolved minerals that have flowed together for billions of years. Water moves at different speeds around river bends, creating a symphony of sounds that changes with each curve. The outer edge of a bend always flows faster than the inner edge, sometimes moving 3 times as quickly. This difference in velocity creates a subtle whooshing sound that experienced river guides can hear from hundreds of yards away. The faster water on the outside carves deeper channels, while the slower water on the inside deposits sediment. This natural process creates the gentle murmur of sand and pebbles settling along the inner banks. Scientists have measured river sounds using underwater microphones called hydrophones. These sensitive instruments detect frequencies far below what human ears can perceive. The low rumble of water moving around large bends creates infrasonic waves that travel through the riverbed itself. These sound waves can be detected miles downstream, carrying information about the river's flow rate and the size of obstacles in its path. The pitch of river sounds changes dramatically with water speed and depth. Fast-moving shallow water creates higher frequencies, producing the familiar babbling brook sound that many find so peaceful. Deeper, slower sections generate lower tones that resonate through the water column. The Amazon River's main channel produces sounds so low that they exist mostly below human hearing range. These deep tones travel for hundreds of miles underwater, creating an acoustic highway that fish and dolphins use for navigation. River bends also create unique acoustic phenomena called standing waves. When fast water hits the curved bank and bounces back, it meets incoming flow to create stationary wave patterns. These standing waves produce a steady humming sound that remains constant even as individual water molecules flow past. The frequency of this hum depends on the bend's radius and the water's velocity. Tighter curves create higher pitches, while gentle sweeping bends produce deeper tones. The sound of water around bends changes with the seasons. During spring floods, the increased volume and speed create a roaring symphony that can be heard for miles. The higher water level allows sound waves to travel over normally dry areas, amplifying the river's voice across the landscape. In late summer, when water levels drop, the exposed rocks and gravel bars create new acoustic patterns as water trickles around obstacles. Temperature affects river sounds in surprising ways. Cold water carries sound waves more efficiently than warm water, making winter rivers seem louder even when flowing at the same speed. Ice formations along the banks act like acoustic mirrors, reflecting and amplifying certain frequencies. In tropical regions, warm water and dense vegetation absorb many sound frequencies, creating a muffled, distant quality to river noise. The geology beneath a river bend influences the sounds it makes. Hard bedrock creates sharp, clear echoes as water strikes the curved channel walls. Soft, sedimentary banks absorb sound waves, producing a gentler, more muted acoustic signature. Rivers flowing over limestone often create unique hollow sounds. As water moves through underground cavities and springs that feed into the main channel. Modern technology allows us to map river sounds from space. Satellites equipped with sensitive acoustic sensors can detect the low-frequency vibrations that rivers create as they flow around bends and over obstacles. This sound mapping helps scientists monitor river health and flow patterns across entire continents. The acoustic fingerprint of each river bend is as unique as a human voice, carrying the story of the landscape through which it flows. Rivers possess an extraordinary ability to create their own weather systems through precise mathematical relationships. The Amazon River generates approximately 40% of its own rainfall through evaporation and transpiration cycles. Water molecules rise from the river surface at predictable rates based on temperature differentials and humidity gradients. Scientists calculate that a single cubic meter of Amazon water can cycle through the atmosphere and return as precipitation up to 6 times before reaching the Atlantic Ocean. The mathematics behind river-generated weather follows elegant patterns found throughout nature. Large rivers create temperature gradients that spawn predictable wind patterns. Cool water surfaces generate high-pressure zones, while surrounding warm land creates low-pressure areas. This pressure differential drives air circulation at speeds that can be calculated using fluid dynamics equations. The Mississippi River system influences weather patterns across an area covering roughly 1.2 million square miles. River valleys act as natural wind tunnels, channeling air masses according to precise geometric principles. The width-to-depth ratio of a river valley determines wind acceleration rates through the Venturi effect. Narrow valleys increase wind speeds exponentially, while wider valleys create more stable atmospheric conditions. The Colorado River carved the Grand Canyon at an average rate of 6 inches per 1,000 years, creating a wind channel that generates its own microclimate system. Evaporation rates from rivers follow mathematical curves that meteorologists can predict with remarkable accuracy. Water temperature, air pressure, and humidity levels combine in equations that determine exactly how much moisture enters the atmosphere each hour. The Nile River contributes approximately 8 billion cubic meters of water vapor to regional weather systems annually. This moisture travels in predictable patterns based on seasonal wind directions and temperature gradients. River-generated clouds form at specific altitudes determined by atmospheric pressure and temperature profiles. Warm, moist air rising from river surfaces reaches its dew point at calculable heights. The resulting condensation creates cloud formations that often mirror the river's path below. Satellite imagery reveals how major rivers create cloud streets that extend hundreds of miles downstream from their sources. The thermal mass of large rivers creates buffer zones that moderate regional temperature swings. Water's high specific heat capacity means rivers absorb and release thermal energy at predictable rates. This creates microclimates where temperatures vary by measurable degrees within short distances from riverbanks. The Seine River maintains Paris temperatures approximately 3 degrees warmer in winter and 2 degrees cooler in summer compared to surrounding areas. Humidity levels around rivers follow exponential decay curves as distance from water increases. Moisture content drops by half approximately every 500 meters from major river systems. This mathematical relationship determines vegetation patterns and wildlife distributions across entire watersheds. The mathematical precision of these moisture gradients creates sharp ecological boundaries visible from space. Rivers influence precipitation patterns through complex feedback loops that scientists model using chaos theory equations. Increased evaporation leads to more cloud formation, which creates more rainfall, which feeds more water into rivers. These positive feedback cycles can amplify weather effects far beyond what simple linear calculations would predict. The Amazon basin demonstrates this amplification effect, where river-generated moisture creates rainfall patterns that sustain the entire rainforest ecosystem through mathematical relationships that connect water, air, and life itself. Rivers move mountains grain by grain, carrying entire continents to the sea in a process so gradual that human eyes cannot perceive it. The Amazon River alone transports over 1 billion tons of sediment annually from the Andes Mountains to the Atlantic Ocean. This sediment contains fragments of granite peaks, volcanic ash, and ancient limestone that once formed towering summits. The Colorado River carved the Grand Canyon by removing approximately 1,000 cubic miles of rock over 6 million years. Each particle of sand in that massive canyon now rests somewhere in the Gulf of California. Water dissolves mountains through chemical weathering that transforms solid rock into microscopic particles. Carbonic acid forms when rainwater mixes with carbon dioxide in the atmosphere, creating a weak acid that slowly eats away at limestone and marble. The Mississippi River system carries dissolved calcium and magnesium from limestone bedrock across 23 states. These dissolved minerals eventually precipitate out in river deltas, forming new sedimentary layers that will become tomorrow's mountains. The delicate balance of this system depends on precise conditions that exist nowhere else in our solar system. Earth's atmospheric pressure allows liquid water to exist at temperatures between 0 and 100 degrees Celsius. Venus has rivers of sulfuric acid that would dissolve any earthly mountain in hours. Mars once had rivers, but its thin atmosphere caused all liquid water to boil away into space. Our planet maintains the exact gravitational pull needed to hold onto water vapor, while allowing rivers to flow downhill at sustainable speeds. Temperature variations across Earth's surface create the weather patterns that drive the water cycle. If Earth orbited just 5% closer to the Sun, increased evaporation would create runaway greenhouse effects that would boil away all rivers. If we orbited 5% farther away, all water would freeze into permanent ice sheets. The 23.5-degree tilt of Earth's axis creates seasons that prevent any single region from becoming too hot or too cold for liquid water to persist. Rivers require a precise balance of slope and volume to maintain their erosive power. Too steep and water flows too fast to carry sediment efficiently. Too gentle, and rivers lose the energy needed to transport mountain debris to the sea. The optimal gradient for maximum sediment transport occurs at slopes between 1 and 3 degrees. This mathematical relationship explains why most major rivers follow similar patterns of steep headwaters, gradually transitioning to gentle coastal plains. The chemistry of river water must remain within narrow ranges to sustain the mountain moving process. Too acidic, and water dissolves everything too quickly, creating unstable landscapes. Too alkaline, and dissolved minerals precipitate out before reaching the ocean. Rivers naturally buffer their pH through interactions with soil and bedrock. Calcium carbonate from limestone neutralizes acid rain, while organic acids from decomposing plants help dissolve resistant minerals like quartz and feldspar. vegetation plays a role in controlling erosion rates and maintaining the balance between mountain building and mountain destruction. Tree roots hold soil in place, preventing rivers from cutting too deeply too quickly. Without plants, rivers would erode mountains so rapidly that sediment would clog river channels and disrupt ocean currents. The Amazon rainforest recycles water vapor so efficiently that it generates its own rainfall, maintaining the steady flow needed to transport Andean sediment to the Atlantic. This mountain-moving process connects to global climate patterns through ocean currents driven by river-delivered sediments. Cold, dense water sinks in polar regions, while warm surface currents carry heat toward the poles. River sediments affect ocean salinity and density, influencing the strength of these currents. Changes in sediment delivery can alter current patterns, affecting weather systems across entire hemispheres. The delicate balance that allows rivers to move mountains also maintains the climate stability that makes complex life possible on our remarkable planet. Beyond our own world, rivers of liquid flow through the darkness of space in ways that challenge everything we thought we knew about water. On Saturn's moon Titan, rivers of liquid methane carve channels through landscapes of frozen water ice. These alien waterways follow the same meandering patterns as Earth's rivers, creating oxbow lakes and deltas made of hydrocarbons instead of water. The temperature on Titan hovers around minus 290 degrees Fahrenheit, cold enough to freeze methane into solid rock-like formations that rivers of liquid ethane slowly erode away. Scientists believe that beneath the icy surface of Jupiter's moon Europa, an ocean larger than all of Earth's oceans combined flows in eternal darkness. This hidden sea may contain twice as much water as our planet holds, kept liquid by the gravitational forces that flex and heat Europa's rocky core. Currents in this buried ocean could create underwater rivers flowing along the seafloor, carrying dissolved minerals and perhaps even life through the alien depths. The ice shell above this ocean stretches and cracks, creating ridges and valleys that suggest the water below moves in predictable patterns. Mars once hosted rivers that flowed for millions of years across its ancient surface. Orbital images reveal meandering channels, braided stream networks, and massive deltas where these long-dead rivers once emptied into vanished lakes and seas. Some of these Martian rivers carved canyons deeper than the Grand Canyon, moving enormous volumes of water and sediment across the red planet's surface. The mineral deposits left behind by these extinct waterways contain clues about Mars's warmer, wetter past when liquid water could exist on its surface for extended periods. Deep beneath the surface of Saturn's moon, Enceladus, geysers of liquid water shoot through cracks in the ice, suggesting underground rivers fed by hydrothermal vents. These subsurface waterways may flow through caverns carved in rock and ice, heated by the same tidal forces that keep Europa's ocean liquid. The water that erupts from Enceladus contains salt and organic compounds, indicating that these hidden rivers interact with rocky surfaces in ways that could support chemical processes necessary for life. Scientists study the composition of these ice geysers to understand the chemistry of the underground river systems that feed them. Venus may have once possessed rivers of liquid water before its runaway greenhouse effect transformed the planet into a hellish world of sulfuric acid clouds. Computer models suggest that early Venus could have maintained liquid water on its surface for up to 2 billion years, long enough for river systems to carve valleys and transport sediments across continents. The extreme heat and pressure on modern Venus would instantly vaporize any liquid water, but traces of ancient river channels might still exist beneath the planet's dense atmosphere. Radar images from spacecraft have revealed features that could be dried riverbeds, though the hostile conditions make direct observation impossible. Even more exotic possibilities exist in the outer reaches of our solar system. Pluto's moon, Charon, shows evidence of ancient water ammonia rivers that once flowed across its surface when internal heating kept these normally frozen substances liquid. Neptune's moon, Triton, may harbor subsurface rivers of liquid nitrogen flowing through caverns of frozen methane and water ice. These alien waterways operate under physical conditions so extreme that they expand our understanding of where and how rivers can exist in the universe. The discovery of exoplanets orbiting other stars has opened new possibilities for river systems beyond our solar system. Planets in the habitable zones of distant stars could host rivers of liquid water flowing under alien skies, following the same physical laws that govern Earth's waterways, but creating landscapes we can barely imagine. Some of these worlds might have rivers of liquid ammonia, methane, or even more exotic substances flowing across surfaces of rock, ice, or crystallized gases. The search for these distant rivers represents one of the greatest mysteries in planetary science, as we work to understand how common flowing liquids might be throughout the galaxy. Each new discovery about rivers on other worlds teaches us something profound about the fundamental nature of flowing liquids and the conditions that allow them to shape planetary surfaces across the cosmos. The rivers we see today are temporary visitors on Earth's surface. In 1,000,000 years, the Amazon will follow a completely different path across South America. Continental drift moves the land beneath flowing water at a pace so slow that entire mountain ranges rise and fall between one river's birth and death. The Colorado River carved the Grand Canyon in just 6 million years, but the rocks it cut through are 2 billion years old. This means rivers are constantly writing new stories across ancient pages of stone. Climate changes will reshape every major river system on the planet. Ice ages return roughly every 100,000 years, locking water in massive glaciers and dropping sea levels by hundreds of feet. When this happens, rivers extend their reach far beyond today's coastlines. The Mississippi once flowed across land that is now the bottom of the Gulf of Mexico. Rivers remember these changes in the sediment layers they leave behind, creating geological records that scientists can read like history books written in mud and sand. The sun grows brighter by about 10% every billion years. This gradual increase in solar energy will eventually boil away Earth's oceans. But long before that happens, the extra heat will change how water moves across our planet rivers in the far future may flow only at night, evaporating completely under the intense daylight heat. Some might flow underground permanently, carving vast cave systems through bedrock as surface water becomes too hot to exist. Continental drift never stops moving. In 200 million years, the Atlantic Ocean will begin closing as the continents reverse their current motion. The Appalachian Mountains will grow tall again as North America and Europe slowly crash together. Rivers will find new paths around these rising peaks, creating drainage patterns completely unlike anything we see today. New rivers are born when glaciers retreat. Volcanoes create new landscapes, and earthquakes shift the ground. The Great Lakes formed only 12,000 years ago when massive ice sheets melted and left behind basins filled with fresh water. Crater Lake in Oregon appeared just 7,000 years ago when a volcano collapsed and filled with snowmelt and rain. These geological timescales show us that river systems we consider permanent are actually quite young in Earth's long history. Some rivers may outlast our planet entirely. Mars once had flowing rivers that carved channels still visible today after billions of years. When Earth's surface becomes too hot for liquid water, some underground rivers might survive by flowing through deep rock layers. These hidden waterways could continue their ancient work of dissolving minerals and carving passages through stone long after surface rivers disappear. The longest-lived rivers on Earth flow through the most stable continental cores. The Finke River in Australia has followed roughly the same path for over 300 million years. It has survived ice ages, asteroid impacts, and massive climate changes by flowing across some of the oldest and most stable rock on our planet. These ancient rivers teach us that water always finds a way to flow downhill, no matter what obstacles time places in its path. Future rivers might flow on worlds we have not yet discovered. Every star in our galaxy could host planets where liquid water carves channels through alien soil. The same physical laws that govern Earth's rivers will shape these distant waterways, creating familiar patterns of meandering channels and delta formations under foreign skies. In the deep future, Rivers may be one of the most common features in the universe, flowing on countless worlds around countless stars. Every single drop of water that falls as rain begins the same ancient journey toward the sea. A raindrop landing on a mountain slope in Colorado will travel over 1,500 miles before it reaches the Gulf of Mexico. Along the way, it joins countless other drops in tiny streams that merge into creeks, then rivers, then mighty waterways that carry the hopes and dreams of continents. This journey connects every landscape on Earth through an endless circulation of water that has continued for billions of years. The water flowing past your window today once fell as snow on ancient mountains that no longer exist. It has been rain in tropical forests, ice in polar glaciers, and vapor in desert skies. Every molecule has traveled through countless rivers, each time carrying minerals and sediments that slowly reshape the face of our planet. The Amazon River alone carries enough sediment to the Atlantic Ocean each year to build a mountain. This endless movement of water and earth creates the landscapes we call home. Rivers connect the highest peaks to the deepest ocean, trenches through gravity's gentle but relentless pull. Water always seeks the lowest point, following paths carved by countless generations of drops that came before. These ancient highways of liquid carry more than just water. They transport the dissolved remains of mountains, the nutrients that feed ocean life, and the chemical signals that link ecosystems across vast distances. A single river system can span multiple climate zones, connecting Arctic headwaters to tropical deltas. The journey from mountain to sea reveals Earth's most fundamental truth about cycles and connections. Every river is both destroyer and creator, wearing down ancient rocks while building new land at river mouths. The Mississippi River has built most of Louisiana through millions of years of depositing sediment from the heart of North America. These river-built landscapes provide homes for countless species and fertile soil for human civilization. Ocean currents carry river water around the globe, mixing the contributions of every continent into one planetary circulation system. Water from the Congo River eventually reaches the Arctic Ocean, Snowmelt from the Himalayas joins the great conveyor belt of currents that regulates Earth's climate. This global mixing means that every drop of water on Earth has been part of every major river system over geological time. The final destination of every river drop is not really the ocean, but the sky. Solar energy lifts water molecules from river mouths and ocean surfaces, sending them back into the atmosphere to begin new journeys. Some drops will fall again within days as rain over nearby land. Others will travel around the world as invisible vapor before condensing into clouds above distant mountains. This endless recycling means that the same water has been flowing through rivers since Earth first had liquid oceans. Rivers teach us that everything on our planet moves in great circles of connection and renewal. The water cycle links every raindrop to every ocean, every mountain to every delta, every moment to every age. In this vast circulation, nothing is ever truly lost, only transformed and moved to new places where it continues the ancient work of shaping worlds. As you drift toward sleep, remember that you are part of this same endless flow, connected to every river that has ever carved its path toward the waiting sea. Every river's story ends in the same place. The Amazon and the Nile, the Mississippi and the Ganges, all pour their waters into the same global ocean that covers most of our planet. This single body of water connects every continent, every shoreline, every river mouth in one continuous embrace. The ocean receives everything the rivers bring. Sediment from mountain peaks settles quietly on the seafloor. Nutrients from distant forests feed tiny floating plants that glow like stars in the dark water. Salt from ancient seas mixes with fresh water from melting glaciers, creating currents that circle the globe like slow rivers within the sea. Deep beneath the ocean's surface, the water that once flowed down riverbeds begins a different kind of journey. Cold, dense water sinks toward the ocean floor and travels along the bottom for thousands of miles. Warm surface currents carry tropical heat toward the poles, while cold currents bring polar chill toward the equator. This great circulation takes 1,000 years to complete one full cycle. Water that enters the ocean today might not return to the surface until your descendants' descendants walk the earth. The ocean holds memories of every river that ever flowed. Limestone cliffs along coastlines contain fossils of sea creatures that lived when different rivers carved different paths across the continents. Sand grains on beaches carry the chemical signatures of rocks that crumbled in mountains millions of years ago. Each grain tells a story of rain and ice, of patient erosion and sudden floods, of the long journey from peak to sea. Even in the deepest parts of the ocean, the influence of rivers continues. Underwater canyons carved by ancient rivers, when sea levels were much lower, still channel deep currents across the ocean floor. These hidden valleys guide the flow of cold, nutrient-rich water that feeds entire ecosystems in the darkness. Life thrives in these deep places because rivers once carried the building blocks of existence from land to sea. The moon pulls gently on all this water, creating tides that breathe in and out along every shoreline. Twice each day, the ocean rises to kiss the land where rivers meet the sea, then retreats to reveal mudflats and tidal pools teeming with life. This ancient rhythm connects the motion of our planet to the motion of its companion in space. Rivers may end at the ocean's edge, but their influence extends far beyond, carried by currents and tides to distant shores. From space, our planet appears as a blue marble suspended in the cosmic dark. The blue comes from all that water, all those rivers and streams, and the vast ocean that receives them. This water makes Earth unique among all the worlds we know, while other planets have ice or vapor. Only Earth has liquid water flowing freely across its surface, carving channels, filling seas, supporting the intricate web of life that includes you. As you rest tonight, that same ocean continues its patient work. Waves roll endlessly against shores around the world. Deep currents carry warmth and cold across vast distances. The water cycle lifts moisture into the sky to begin new journeys as rivers yet to be born. In this quiet rhythm of flow and return, of journey and rest, you can hear the heartbeat of a living planet, All rivers go to rest in the ocean's embrace, and all water returns eventually to the sky. In this endless circulation, nothing is ever truly lost, only transformed and renewed. You are part of this same ancient flow, connected to every drop that has ever fallen as rain or flowed as a river toward the waiting sea. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.